Welcome back, dear students. Under Algebra number theory, we are in Unit 5, Classical Theorems and Multiplicative Functions. We had already completed 3 lectures on Wilson theorem. So we are into the lecture number 4, where we are going to study about the theorem of FERMAT'S and its proof, and followed by problems in lecture 5 and 6. So let's get into the presentation. So before we get into the presentation, we'll just have an overview of about the famous mathematician Fermat. Pere de Fermat, during the period 1607 to 1665, he was a French mathematician, whereas John Wilson was a British mathematician. His notable contributions to number theory had given rise to the Little Fermat's theorem in 1640. There was actually 2 theorems, Fermat's theorem. So there was just for a differentiation purpose. So just to differentiate, this theorem was named as Little Fermat, because there is another theorem called as Fermat's last theorem. So this Little Fermat's theorem was done in 1640. Fermat's Little theorem is a fundamental theorem in which the elementary number theory is being done to compute powers of integers modulo prime numbers. What we did under Wilson theorem was factorial numbers. Here we will be having powers of integers. Okay, let's move on to the presentation. First, we'll start with the statement of lemma, which is applied in Fermat's theorem. So let P be a prime and A be any integer such that P does not divide A. Then the least residues of the integers A dot 2A dot 3A dot so on up to P minus 1 of A modulo P are a permutation of the integers 1, 2 and so on P minus 1. So this is the statement of the lemma. You know what are the permutation of numbers? Permutation is a function which maps function to itself, right? So now we'll be having modulo P. P is a prime number. So this theorem also holds for a prime number. So we'll start with the proof for the lemma. The proof consists of 2 parts. First, we shall show that IA is not congruent to 0 mod P for I lying between 1 to P minus 1. That is the first equation. Then we show that the least residues of IA and JA modulo P are distinct if I is equal to J. That is, I and J are between 1 and P minus 1. To prove 1, so what is actually 1? IA is not congruent to 0 mod P. To prove that particular congruent relation, suppose that IA is congruent to 0 mod P. Then what can I say? Then I say P divides IA. Correct? When will I get a reminder as 0? When will I get a reminder as 0? When the modulo number perfectly divides this particular number, I'll be getting a number 0. So that's why I'm saying that P is dividing IA. But P does not divide A. So P does not divide I. This is impossible because I is lying between 1 to P minus 1. Therefore, IA is not congruent to 0 mod P. Clear? So to prove 2, suppose that vice versa, that is IA is congruent to 0 mod P, where IJ lying between 1 to P minus 1. Since P comma A, that is the GCD, which is equal to 1, they are relatively prime numbers. So which is equal to 1, so which implies I is congruent to J mod P. So now we move on to the statement of the Fermat-Little's theorem. If P is a prime and A is any integer, not divisible by p, then a minus p is congruent to, a to the power p minus 1 is congruent to 1 mod p. This statement can also be written as, let p be a prime and a be any integer such that p does not divide a, then a to the power p minus 1 is congruent to 1 mod p. In Wilson theorem, we had p minus 1 factorial is congruent to minus 1 mod p. In Fermat's little, we have it as 8 raised to the power p minus 1 is congruent to 1 mod p. So let's move on to the proof. By the lemma, the least residues of the integers 1, a dot 1 into a can be written as 1 into a, 2 into a, 3 into a, and so on, p minus 1 of a are the same as the integers 1 dot 2 dot 3 etc. up to p minus 1. So when taking a out, a is just multiplied to all the. So in some order, so their products are congruent modulo. So when I'm taking the product of these numbers, both are the same, they're same. So left as well as your right. So on the left hand side, what am I having? A dot 2a dot 3a and so on, p minus 1 of a, right, is equivalent to 1 dot 2 dot 3 so on, p minus 1 of mod p. Now what can I do here? Now this can be written from my right hand side. Just observe my right side of the congruent symbol. How can I represent 1 dot 2 dot 3 and so on, p minus 1? Can I write it as p minus 1 factorial? Yes, I can. So factorial number can be written as 1 into 2 into 3 etc. up to that particular number. Same way, till p minus 1 I had written starting from 1. So I can replace that as p minus 1 factorial mod p. What is happening in my left hand side? Left hand side, can you just observe, because a is common to all the factors, right? So I'm just taking a as a common. So how many times a has come? A raised to the power p minus 1 times it has come. Able to understand? So a 2 times a square I will write. See, for example, let me consider these two. Here I have a. Here this a can be written as 1 into a, right? 1 into a and 2 into a. Suppose if I'm having, how many a's I'm having? It's product, right? So this from here, from the first term I'll get 1a, first single a, and from the second term I'll get another single a. So a into a is square. So it is equivalent to the number or coefficient before a. Same way for 3a. 3a also I'll be writing a into a cube. Same way for this number of terms I can write a raised to the power p minus 1. So same way. So again 1 dot 2 dot 3 so on, p minus 1 can be written as p minus 1 factorial and a to the power p minus 1. So both sides I'm having p minus 1 factorial, which gets cancelled, and a power p minus 1 is congruent to 1 mod p. Therefore, the result a to the raised to the power p minus 1 is congruent to 1 mod p can be written as equivalently as a to the power p is congruent to a mod p. So both the results are the same. Note, by applying Fermat's little theorem, the properties of congruences, we can find reminders of certain numbers a power m when divided by p. There is no ultimate need that there should be minus 1 of that. So we can have it as 2 raised to the power p. So always remember, a raised to the power p minus 1 is congruent to 1 mod p is equivalent to a raised to the power p is congruent to a mod p. So hence the proof of Fermat's little theorem. Thanks for watching. We'll continue in the next lecture.